Hello everyone, and welcome to Group SH04's capstone presentation. Our group consists of 3 members, myself, Mark Godden, Matthew Orr, and Ethan Pereira. Our project is fully electrifying a 2016 Chevrolet Camaro with the use of a switch reluctance motor, or otherwise known as an SRM. This project contains both electrical and mechanical aspects, and our group is focusing on the mechanical side. The number of electric vehicles on the road increases more and more each year, and it is clear to see that electric vehicles might overtake vehicles with an internal combustion engine as the future of transportation. One of the problems with the current high-performance electric vehicle design is their use of permanent magnet motors. Permanent magnet motors are much lighter and produce much more power than an internal combustion engine. However, they still have their drawbacks due to their use of rare earth metals in their design. Rare earth metals result in the motor being expensive to manufacture, as well as being harmful to the environment due to their extraction and mining process. This brings us to the switch reluctance motor. The SRM was originally used for mines and nuclear reactors, but it has since been adapted for automotive purposes. They have great performance in high-speed applications, and when compared to permanent magnet motors, they are much cheaper to manufacture, and they have much less of an impact on the environment, as they do not use rare earth metals. The reason that we chose the 2016 Camaro as the vehicle to electrify is due to the group's involvement with the EcoCar team. The 2016 Camaro was used in the EcoCar 3 competition, where it was turned into a hybrid electric vehicle. The vehicle is currently in the McMaster Automotive Research Center as a rolling chassis. This gave our group the ability to go in and take the necessary measurements of the car and determine where we could place our components and what modifications needed to be done to the frame of the Camaro to fit these components.
In order to fully electrify this vehicle, we first must select the components and determine their placement within the vehicle. The components selected are as follows: a switch reluctance motor, a motor inverter for the SRM, an 11 kilowatt-hour 300-volt battery pack, a Brusa high-voltage charger for the battery, a Brusa high-voltage to low-voltage converter.
With the component selection complete, our team moved on to the architecture selection process, where we created 3 different architectures to study. The difference between architectures was the differing packaging solutions and the number of electric motors used. Once the weight studies, space claim, and drive cycle simulations were complete, our team, along with the electrical team, decided on using an architecture with one SRM packaged in the rear of the vehicle, ahead of the rear axle, and package the high voltage battery in the front of the vehicle in the engine bay. This architecture was the lightest, had favorable weight distribution, and also had similar performance to the dual motors in our simulations. For our thermal system design, we used the components' known and tested thermal limits to design just 2 cooling loops for all the components in the vehicle. In the mount design process, we aim to keep everything as light, simple, and reliable as possible to make sure the design is feasible and can be used as a research vehicle. For the SRM, we used a combination of sheet, plate, and square tube aluminum 6061, along with rubber dampers to mount it to the rocker panels and floor of the vehicle. In the front of the car, the high voltage battery enclosure uses hot rolled steel and steel alloys to mount our 11 kilowatt-hour battery to the frame of the Camaro.
A MATLAB Simulink model was developed for the electrified Camaro. Each component modeled based on their specifications. This is the electrical plant where the high voltage battery, the SRM, and the high voltage to low voltage Brusa converter are modeled. Once these physical components have been modeled, a control strategy must be developed. This consists of torque determination of the motor based on the accelerator pedal position and regenerative braking based on the brake pedal position. When the physical components and the control strategy are finalized, simulations can be run to determine the feasibility of one's design. The blue line is the target speed of the vehicle, and the yellow line is our actual speed of the vehicle. Having perfect matching is not possible, but if your output is close, you can be confident in your model and design.
This concludes our project, the integration of an SRM into a 2016 Chevrolet Camaro. Thank you very much for watching, and we hope you enjoyed our video.